Okay, recording device has been initiated yet again. What are we doing today? Today is Friday. So we're going to do a little Riemann sums today, a little bit on Wednesday because you're off on Tuesday. What a racket. And don't forget, on Monday, what are we doing? Going over the last one, right? Don't get excited. It's not a new test. Going over the last one, you're going to get it back. Alrighty, so today's topic is really goes from Friday to Wednesday. Holy cow. Alrighty, so let us begin. Riemann sums. Alright, let's take a look at an example, a simple example of Riemann sums. Dun, dun, dun. Okay, loading. What? Yeah, that didn't work. Hang on. Something's wrong with my desktop today. Okay, there it goes. So, alright, kindly consider the following. Here's a simple example, okay? What if I want to find this integral, this definite integral, the area from 0 to 5 in x for y equals x, the area under y equals x bounded by the x-axis. That's what that symbol means, right? Okay, I'm going to use a right Riemann sum to estimate this answer. I'm going to use a right Riemann sum on the function x with 5 equal divisions. What does that mean? Any ideas? Matt? Okay, so you're going to take the height of the rectangle from the right endpoint of delta x, right? Of the width of the rectangle. Okay, so let's do that. Why don't we draw something like this? Let's see. I'm going to draw some axes. Zing, zing. Bring this up a little bit. Okay, and the line y equals x is very simple. What is it? It's just a line. Diagonal line, 45-degree line through the origin. Let's say it's this. Okay? And what I want to do is break this up into 5 equal rectangular areas, estimating the area under the curve. Okay? So let's say this is 0, and let's say 1, 2, 3, 4, 5. This is 5. Okay? So this is y equals x. This is x, this is the axis, and this is the y-axis, right? Okay, and of course, clearly the y intervals are the same, because y equals x. So let's draw the right rectangles. Now you can have left rectangular sums. Have you done right rectangle? Left rectangles? Mid sums? Mid rectangles? Trap sums? Right? Trapezoidal? Have you done Simpson's rule? Well, it's rectangles except the top is a parabola. It's like, well, actually, it's more like a trapezoid, but the top isn't a line, it's a parabola. No? Oh, you lead a sheltered life. Yeah, well, maybe not. Maybe not. Maybe not. Maybe not. Okay, so let's draw these rectangles.
No, it's not like that.
Now, this is the right rectangle, right. Well, this isn't quite, my delta x isn't quite uniform. Oh, well, we'll live. No, right rectangles. The right side of the base is where you take the height. Okay, all right. Not yet. Start easy. Work our way up. We got 5 weeks for this, right? For this topic. Yeah, that's pretend they have a uniform delta x. Okay. Yeah. What is the size of delta x? I'm going from x equals 0 to x equals 5, right? 0 to 5. In 5 equal pieces. So what's that? The 1 unit across, right? In general, what is that? Well, that would be delta x is b minus a over n. What does that mean? What did I just say? All right, so your domain 5 minus 0 divided by the number of rectangles you want, right? So 5 minus 0 over 5 would be 1 in this case. Delta x isn't always 1, but it is 1 in this case. Okay, so how do you estimate the area? Now let's pretend for a minute that we don't know the area under this curve. By the way, it's sort of silly to do an integral here. What is the area under the line? Forget the rectangles for a minute. Isn't this a triangle? Do you really need an integral for this? No. So what's the base of the triangle? What's the height? And so what's the area of a triangle that's 5 by 5? 25 over 2, 12.5. Okay, now let's say we don't know the answer. Okay? Let's pretend we don't know the answer. How do we estimate this answer using a right rectangular sum? All right, well, let's see. A right sum with 5 equal intervals on the function x from 0 to 5. All right, I guess I should specify that. From 0 to 5, right? That's just another notation. But we realize that this has to do with anti-differentiation, right? But for the longest time, there was no connection between the derivative and the antiderivative. Nobody knew that the answer to this problem had to do with the antiderivative. There were 2 separate branches of calculus. One about slopes, derivatives, and one about areas, area under the curve. And they never knew this connection. That's what this unit is about. Eventually we're going to get to the fundamental theorem of calculus that connects the area under the curve with the antiderivative. For hundreds of years, nobody had any clue that this had to do with anything to do with the derivative.
Why not?
Because they just didn't.
Why did they ask?
Well, they did, but they didn't find the answer for a long time.
Why not?
Because they did it this way.
I was doing one thing and he was doing another thing. It's like, I got 4. It's like, I got 4 too. It's like, oh,
Well, eventually, right. That's what we're going to do. That's exactly how it's going to turn out in class. We're going to see that happen.
I could have done that in 5.
Well, okay, sure. Now, what is the area of the first rectangle? What's the area of any rectangle? Base times height. The base is how long? 1. The height is 1. The base is? The height is? The base is? The height is? Okay, now what is it? It's f. Technically, it's f of 1 times delta x. It's f of 2 times delta x, right? Let's write that down. Base times height. Base times height. That's what I'm doing, right? I'm going to run out of room real fast here. I need 5 rectangles, right? Base times height. And, whoops, plus. Keep on going. Plus base times height and base times height, right? So did I get everybody? Look at this. F times delta x. F times delta x. F times delta x. Do you see this notation? F times dx. This is the height of the Riemann rectangle. This is the width of the Riemann rectangle. Okay? That's why you have a dx. And you must have a dx, or d something, right? This is the base, this is the height of every rectangle. But what's the difference between dx and delta x? Delta x is like the gross width. Dx is a fine width. In other words, as n goes to infinity, delta x goes to... Now, if b and a are constant and n goes to infinity, delta x goes to? 0, exactly. So this is the limit of delta x. As n goes to infinity, delta x goes to dx. Now, this is called an infinitesimal. All right? It's infinitely small. It isn't 0. The limit is 0, but it isn't physically ever 0. Right? The idea is this. What if I break this into 10 rectangles instead of 5? What if I break this into 100 rectangles instead of 10? What if I break this into 1,000 rectangles instead of 100? It's more accurate because what's going on is you have an overestimate here, right? But as you have more and more rectangles, that overestimate gets smaller and smaller and smaller, as we'll see in a minute. Okay? Exactly. So the error goes to 0 too. Ooh, interesting. All right, so let's figure this out. Delta x is 1. I'm going to just factor that out, right? 1 times f of 1. Well, the function is y equals x, so f of 1, y equals x is 1, right? So f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5.
Why did they multiply that?
Well, I factored out the delta x. I'm just making the point, that's delta x. I factored it out. Delta x is 1, right? Okay, so what's 1 plus 2 plus 3 plus 4 plus 5? 15. All right, so there's my estimate for the area bounded by that triangle. But remember, the triangle area, you just told me was 25 halves, or 12.5, right? So clearly what we got here is an overestimate. So what happens? when you use right sums to estimate the area, and the function is increasing, you're going to find that right sum is an overestimate. Okay? So let's write that down. If f prime is positive, R sum overestimates.
What if it's,
And by the way, left sum underestimates. We'll find in a minute too. And vice versa. If f prime is negative, then R sum underestimates and left sum overestimates. You're going to see all of this by doing a bunch of examples, okay? Okay, that's a U, okay, I guess. Alrighty, so that's something we're going to see happening. Okay, so as n goes to infinity, the number of rectangles goes to infinity, they get thinner and thinner and thinner, delta x goes to 0. These errors become smaller and smaller and smaller. You're going to get the answer that you wanted. By the way, is the answer really 12 halves? 12.5, sorry, 25 halves? What if we did it this way? What's the antiderivative of x? X squared over 2. And according to the fundamental theorem of calculus, which we haven't even talked about yet, really, well, how do you evaluate this? Plug in what? 5, so that's 25 halves. And then just subtract what? Plug in 0.
bracket thing, is that up there in the
No, this just means plug in 5, plug in 0, and subtract. That's shorthand for this. And so you do get 25 halves at 12.5. So my estimate should be 12.5. My estimate is a little bit too big. How do I improve it? Make more
make more
rectangles. Okay, let's make more rectangles. Let's do it again. Let's estimate this area. Whoops. With an R sum that has 10 equally wide rectangles, okay, on the function x from 0 to 5. Okay? Evaluate it from 0 to 5. So what do? Well, you draw it again. Let's draw it again. Okay, here we go. All right, now we're going to break it up into 10 equal pieces, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But this is still 5. So this is 1. This is 2. This is 3. This is 4. Okay? And this is y, and this is the origin. Okay. So let's draw the curve. Actually, we could do this too. Let's say it's supposed to be a 45-degree line, right? So let's say like that. All right, so can we draw it? Let's see if this drawing comes out a little better. I don't know. That's too wide. Yeah, I can't get this to draw uniformly. I don't know why. Dang it. What is that? Okay, just give me one rectangle. God bless. All right, well, anyway, you get the idea, right? So do I have to draw them all?
Yeah.
Do you see that the area above the curve, which is the overestimate, the error is actually getting smaller, is the point, okay? So I'm going to draw them all. Here we go. So what do you get? You get that R sum, I need a different device. R sum with 10 equally spaced rectangles, finding the area under x, y equals x from 0 to 5, from x equals 0 to x equals 5, is what? It's delta x times what? I'm factoring out the delta x to start with. F of who? Who's the first height? 1/2. Plus f of... This height is f of 1/2. This height is f of 1. This height is f of 1.5 and so forth. Okay, so I'm going to say 1 and f of... let's write it 3/2. Okay, plus f of 4/2, which is 2, plus f of 5 halves plus f of 6 halves, which is 3, plus f of 7 halves plus f of 8 halves, which is 4, plus f of, dang it, 9 halves, plus f of 10 halves, which is 5. Okay, so what is it? Well, delta x is what now? Right, delta x, remember, delta x is b minus a over n. That's 5 minus 0 is 5 divided by 10. 5 divided by 10 is 0.5, or 1/2, right? Okay, so the rectangles are thinner, and we have more rectangles. So it's just 1 times f of 1/2, f of 1, well, y equals x is f. So it's just 1/2 plus 2 halves plus 3 halves plus 4 halves plus 5 halves. That's a half. Plus 6 halves. I might as well keep it all with common denominators, right? Plus 7 halves plus 8 halves plus 9 halves plus 10 halves. Okay, so, is it?
45.
Well, yeah. What's the sum of the first 10 consecutive integers? Do you notice? What's the sum of n as n goes from, well, wait, I should say it this way. What's the sum of I as I goes from 1 to n? Meaning 1 plus 2 plus 3 plus all the way up to n. Do you see a pattern here? Here we got 15, right? 1 plus 2 plus 3 plus 4 plus 5. The first 5 consecutive integers gives you 15, right? If you add the first 2, you get 3. If you add the first 3, you get 6. If you add the first 4, you get 10. If you add the first 5, you get 15. Is there a pattern going on? And you just told me if you add the first 10, you get 55. Is that right? You don't know this pattern? This is n times n plus 1 over 2. Never heard of this? No? Because if n is 10, what's n plus 1? If n is 10, that's 10, and this is 11, right? 10 times 11 is 110 divided by 2 is 55, right?
What if we don't start at 1?
Well, we're going to start at 1. I'm making this easy. You can do this with right sums. You can do this with left sums. You can do this with a equals 0. You can do this with a not equal to 0. But the easy case is if you do right sums and a equals 0, you always start with a 1. Haha. You always start with a 1. 1 or 1/2 or 1/3 or 1/4. Okay, I'm trying to make it easy. Okay? As it turns out, this is a well-known sequence, or a series, sum of a sequence, right? This is known as Gauss's series. Gauss was a great mathematician, but in kindergarten, he really bugged his math teacher a lot. And she got really pissed off at him one day. And being Swiss, they had dunce caps and they had been sit in the corner. And she said, look, don't bother me. Leave me alone for a while. Add up the integers from 1 to 100. Add up the whole numbers from 1 to 100. It'll take you a while, right? Leave me alone. Go away. Right? He comes back like 2 minutes later. He says, 50-50. How did he do that? He noticed this pattern. 1 plus 2 is 2 times 3 over 2. 1 plus 2 plus 3 is 3 times 4 over 2. 1 plus 2 plus 3 plus 4 is 4 times 5 over 2. Isn't it? 1 plus 2 plus 3 plus 4 plus 5 is 5 times 6 over 2. That's what I'm saying. 5 times 6 over 2. That's all. You need this pattern. We're going to need this, okay? So anyway, this is 55 halves. And 55 halves is what decimal? Oh yeah, and don't forget, yeah, we have the 1/2 in front. Whoops. Yeah, this is the parentheses, and there was a 1/2 in front, right? Whoa, got a little crazy. Okay, so that's really 55 quarters then, isn't it? So I'm adding, I have common denominators, so the top is 55, the bottom is a half, and I'm dividing by 2, so I get 55 quarters, and 55 quarters is, how much? 13.75, right? All right, now notice what's happening. We started with an estimate of 15, right? We know the answer is supposed to be 12.5, but we're not supposed to know that. And now our estimate is 13.75. Is it getting better?
By half.
All right, as n gets bigger and bigger and bigger, the number of rectangles, the error gets smaller and smaller and smaller. This, you're approaching this as a limit from above. This is a limiting process, okay? All right, so can we generalize this a little bit? Let's see. Well, let's make this even more general. I'm going to do this a little more algebraically. All right, try this on for size. Let's write this more in general. A right sum with n equally spaced rectangles for f of x from a to b is what? Didn't we factor out the delta x? Right? Last time? Can we do that? Yeah, why not? And then we're going to say it's f of a plus delta x. Now let's see, is that true? The first height was f of 1/2. A is 0 and delta x is 1/2. So is that f of a plus delta x? What's the next one? F of a plus 2 delta x's. F of a plus 3 delta x's, yes? Okay, let's write it that way. I will write this in general for any function, not just f of x equals x. So plus f of a plus 2 delta x's plus f of a plus 3 delta x's plus, keep on going until you get to f of a plus n delta x's, which happens to be b, right? If delta x is b minus a over n, what's n times delta x? It's b minus a. But if a is 0, as in our example, that's b, isn't it? All right, now, you can do this for any a and any b. You can do this for any function. You can do this with left sum, right sum, chop sum, whatever. But I'm making the easy case. Right sum, starting with a equals 0, okay? Just so you see what the pattern is, okay? I'm looking at the pattern for right sum when a equals 0, just to make life easy, okay? All right, so can I rewrite that in terms of a equals 0? Okay? Let's rewrite that in terms of a equals 0. R sum with n equally spaced rectangles for f of x, whatever f of x is. It doesn't have to be y equals x, right? I'm trying to generalize it so I can get a formula for the answer. All right, is what? It's delta x, the width of each rectangle, right, times every height. But if a is 0, that's just f of delta x, f of 2 delta x, f of 3 delta x, right? Now, let's go back to our original question. What's f of delta x if f is y equals x? This is f. What's f of delta x? A is 0. What's f of 2 delta x? What's f of 3 delta x? If this is f. What was it before? 0 plus a half. F of 0 plus a half was a half. That's y equals x, yes? When this was 0 plus 2 halves, that was 0 plus 1. F of 1 was the next height, but f is y equals x, so the height is 1. All right, so all I'm saying is that I get this. Right, this is in general for any a and any f. This is if a is 0 and f is y equals x. Right, going back to the original equation. All the way up to, now remember, if a is 0, well, I don't know. Delta x could be any delta x I want depending on n, right? Okay. So this is really the problem that we were doing, right? Now, what makes this answer better and better and better? If n goes to infinity, right? Let's take the limit. What's the limit as n goes to infinity of this thing? It's the limit, as n goes to infinity, of this thing. I'm doing this in general for any delta x. It's the specific problem we started with, a equals 0 and y equals x, the function, right? But I'm trying to generalize this a little bit more for any n, any delta x. Okay, what does that mean? Well, I could write that as a sum, can't I? Notice, all right, let me write that as a sum. You have delta x, you have the limit, as n goes to infinity, of delta x plus what sum, times what sum. You can write that as a sigma notation.
That's the sum of, okay, we do that thing, so it's like, start with
Well, how about, well, am I starting at 0? What are the coefficients? 3, 2, 1. 1, 2, 3, over up to n, right? So you can use any variable here you want. I'm going to use k. K starts at 1, and it goes to n, and it's k times delta x. That's the same as that, right? Okay. K goes from 1 to n. Well, remember, this is a discrete function. It goes up by 1. 1, 2, 3, 4. It goes up by 1 every time. Remember we did sequence in series? Discrete functions in this case in K would be just whole numbers or integers, whatever. Okay. Whole numbers or natural numbers, I should say. Well, notice, could I multiply, could I bring this delta x in? Let's see, let's write this. The limit as n goes to infinity, or take it out for that matter. See, delta x is not affected by k. Delta x is affected by n, though. As n gets bigger, delta x gets smaller, right? This is b minus a over n. So I could put it in or take it out. I'm going to take it out. Delta x squared times this sum. But didn't we just talk about this sum? This is 1 plus 2 is 2 times 3 over 2. 1 plus 2 plus 3 is 3 times 4 over 2. 1 plus 2 plus 3 plus 4 is 4 times 5 over 2. This is, if you're going up to n, it's going to be, where is it? It's going to be delta x squared. Wait, I didn't do the limit. Wait, hang on. The limit, as n goes to infinity, of delta x squared times this sum. But we just said that sum is n times n plus 1 over 2. Didn't we? Okay. Now what's delta x? Remember that delta x is b minus a over n. But in our example, that's if k goes from 1 to n, whatever n is. Again, 2 plus 3 over 2. This just represents 1 plus 2 plus 3 plus 4 plus 5 plus 6. That's the sum. Okay? Now, what is delta x? Delta x is b minus a over n, but in our example, b was 5, a was 0, and n is n, so that's just 5 over n. 5 minus 0 is 5, 5 over n. Okay. I'm writing this so I can take the limit in n. I'm trying to figure out how to make this a limit in n, okay? So this is 5 over n squared times n plus 1 over 2. Do you see anything familiar here? Remember what the answer was supposed to be. What was the area of the triangle? Base is 5, height is 5. How do you get the area of a triangle whose base is 5 and its height is 5? Base times height over 2, 25 over 2. Do you see a 25 in here?
Yes.
Do you see a 2 in here?
Yes.
They're constants, so they're independent of n, aren't they? Okay, I'm going to pull them out. 25 halves, the limit, as n goes to infinity, of n squared plus n over n. Do you know how to do this limit?
Okay. Scales factor, simplify.
Oh wait, I did a boo-boo. This is an n. Wait. This is n. This isn't n. This is right. What's wrong? Squared, sorry. Whoops. Remember, we got how to do these limits. Top heavy, bottom heavy, equal degree. Which one do we got? Equal degree. The limit is the coefficients, not 0. 1. So you get 25 halves. Top heavy goes to infinity. Bottom heavy goes to 0. Equal degree is just leading coefficients. 1 divided by 1. Look, we got exactly 25 halves. What is that? That's the area under the curve, isn't it? This is how they used to do definite integrals, when they didn't know it had anything to do with anti-differentiation. Hundreds and hundreds of years, nobody knew it had anything to do with right? Hundreds and hundreds of years went by before integral calculus and differential calculus met as one subject. Because they always did it this way. They did it geometrically with rectangles. What? No? Alrighty. So it stands to reason then that we could do any integral we feel like this way. Doesn't it? Let's think about that. Well, I'm saying, do you see what I'm doing? I'm justifying the power rule of integrals, right? I'm justifying what you know about this. Wait, if it's n, what do you get? X to the n plus 1 over n plus 1, right? So when it was 1, you got x squared over 2. When it's 3, you get x cubed over 3. When it's 4, you get x to the 5th over 5. I'm going to show that that pattern makes sense doing it this way. That is where this comes from. Where did you find out this? How did you figure this out? When you first saw this, how did you figure this out? Someone just told you. It says, oh yeah, by the way, it's x to the 5th over 5. Yeah, tomorrow it's x to the 3rd over 3, you know. Told you the rule, but without any reasoning, right? This is the reasoning. This is where it comes from. You've got to understand this stuff. It comes from Riemann sums. Guys, if you never did this with Riemann sums, you never did Riemann sums. 1. And you never justified the power rule for anti-differentiating power functions. Okay? So did you do either of those things last year? No. So we got to do it. Okay? And I'm going to leave it at that for today.
Good.